Okay, good afternoon, everyone. I see three of you. So if you are into modeling natural resources skill session, you are at the right place. Of course you are. This is the part one of the two sessions that I'm going to deliver. The next session is next Tuesday at the same time. I'm gonna introduce myself briefly. My name is Sanoar Rahman. I know a couple of you already know me. I am a TA for EPICS, and this is my second semester with EPICS. I'm also a PhD student in agricultural and biological engineering, also part of ecological and science, ecological, okay, let me repeat that. Ecological science and engineering program. Okay, we always know it's ESC program, but never try to elaborate anyway. So if you can take, since we have only a few students joining today, so if you can take a few minutes and introduce yourself and maybe share a thought like, why did you choose this skill session? I know you might be part of the NRES program or environmental, engineering program, something of that sort. So whoever wanna go first.
Okay, I can go ahead. So yeah, I chose this session because this is of interest to me and the project I'm working on. So I'm in the WRM team. I know Dr. Bowling, who's one of our advisors, does some work in wetland we're working in with piezometers, which I think could be related to what we're going to talk about today. And I think it was interesting when she first explained it to me, and interested to learn more about natural resources modeling.
Okay. Next.
I can go. So my name is Arsh, and I'm part of the GAQT team. So I just found this quite interesting. I don't know much about it, but it sounded interesting, and our team does work with biogas and solar, so I thought, why not?
Okay, sure. Abigail.
Hi, my name's Abby. I'm part of the EWB team. I honestly just saw the skill session and I thought it sounded interesting. We're doing stuff with like water distribution, so I thought it could relate. So yeah, that's kind of it.
Okay, sounds good. Okay. Okay, do we have anyone else? Okay, since I am in the presenter mode, so I don't see the number of participants now, but anyway, so I'm guessing there is no one else participating. So moving on, no, sounds good, all great reasons. Yeah, I hope you're gonna, learn something about modeling natural resources from this skill set. I know this would be a very basic intro to modeling. And I'm going to use the chat function quite a bit, as well as if you want to ask any questions, stop me at any moment, and I'll be happy to answer those questions. Okay. So what comes to your mind when you hear the word model? Let me rephrase that again. Like, what visual image pops in your head when you hear the word model? Let me guess, something like this, right? Because this is the, this is the model and modeling we know most, right? Okay, so however, there are other kinds of models as well, right? And there are other kinds of modeling too. So these are scientific models. So unfortunately, today we are going to talk about this sort of models and modeling, okay? And the objective of this session is to discuss scientific modeling. What are some of the different types of scientific modeling? We'll learn the basics of mass balance equation in this skill session, as well as, I'm going to go over some generalized modeling processes in this session. What are scientific modeling? So scientific modeling is basically the generation of physical, conceptual, or mathematical representation of a particular phenomena or a particular system. So there are a few keywords here. physical, conceptual, or mathematical representation. Okay, so representation of what? Representation of a particular phenomena. Some of the simplest examples of these physical phenomena or these phenomena are, say, weather. It can be volcanic eruptions. It can be any physical processes, right? So the scientists and engineers, people like you and me, we can represent these phenomena physically, conceptually, or mathematically. Okay. So what scientific models are? They are abstract, of course, they are not real. They simplify the system and explain and predict the behavior of natural real system. Okay, and used in a variety of scientific disciplines. Okay. So next I'm going to talk about the types of scientific models. So scientific models can be broadly divided into three categories. First of all, the visual models, like the one that I have. This can be from anything from simple illustration, like the one that I'm showing right now, or it could be a simple figure. Okay. Then we have physical models. Okay. So one example of physical models are like the one that I am showing here, DNA double helix model. So this is basically physically you construct something to overview of something that is not naturally possible, right? Because the DNA double helix, these things are very small, very tiny, and it cannot be seen in natural eyes. Okay, so that's why you do this, construct those physical models, and in school, colleges, and universities, you're gonna see this kind of models, right? Then I have the mathematical models. Okay, so mathematical models usually describes a system by a set of variables. Okay, and a set of equations. So you'll need a bunch of equations. Okay, this equation will establish the relationship between the variables. Okay, so say you have a natural system, there are some influxes and outfluxes. So these are the variables for you, and you use some sort of equations to relate these variables. Okay, like the one in this illustration they did. They tried to use some equation to see what are the inputs and what are the outputs. Okay. So why do what are the advantages of doing simulation and modeling? Okay, think of something like that. Why would people use simulator when they are learning, flights? Like the pilots learns flights, why do they use simulator? Right? They don't use directly the plane at the first place, right? Because there are risks of doing that. Okay. There are other purposes of scientific modeling, and of course you can visualize system or an object. Okay, think of the solar system model. Okay, so in the solar system model, you are visualizing the whole solar system, which you cannot do in naked eye, right? You hardly can see all the planets. You cannot see all the planet in naked eye. So you can visualize, and of course you can study objects that are too small or too large, like the DNA double helix model I have shown. There are like protein models, there are like cell models, biological cell I'm talking about. So these are some of the things. So if they are too small or too large, like solar system, you cannot visualize, you cannot study the object easily, right? That's why we use these models in school, colleges, and universities and whatnot, even in museums. Okay. Then the third thing, there are predictive models, and what they do, they describe hypothetical behavior and forecast the future. Okay. So can you guys tell me one example of this kind of models? I'll be asking questions, so I'd like to, it be a bit interactive. So if you can give me an example of, forecasting. Yeah, go ahead.
for the future models, maybe like a climate change prediction model?
Exactly. Climate change, even the weather forecasting, like what would be the weather tomorrow, there's predictive model, right? We are predicting, and this is some sort of modeling as well, okay? Then also, like, disease outbreak, like in the pandemic situation that we are going through right now, like we need to predict, like, how long it's gonna last and how many people are getting infected if we, get infected at the same rate, something like that. So to better understand the system and the processes, we use these models. Then I also have a illustration or a figure on the bottom. So this is from the groundwater level diagram. So in this diagram, I have shown data from 2019 to 2030. Okay, so 2019 to 2030, that's 10 years of groundwater level data. Okay, so this is basically showing you depth of groundwater level or groundwater table from the surface, land surface. So this way you can see a trend, right? So this is a future trend a scientist or an engineer showed right here. So they are showing if we continue extracting the water from this groundwater system, the groundwater level is going to go down in the future. Okay, so that we can act upon these changes. Okay. So to make management decision, water resources management that I'm talking right here. So for those things, the stakeholders need this sort of information, right? Any questions so far about the purposes or, these things? Okay. If not, then I'm gonna go to my next slide. So there are limitations of scientific modeling or scientific models as well, right? So they are only models, not the real thing. So you cannot fully represent the natural thing or the real thing all the time in the models. In fact, most of the models, they have some sort of assumptions, right? So they predict something, they assume something, and based on that, you construct the model. So everything is not real. The second thing is scientific models are not complete representation. I mean, kind of, I'm iterating my first point. So we cannot fully represent all the things. Like for the groundwater model, you know some of the basic flow parameters, some of the basic flow that's going on after you receive precipitation, but you do not know everything that is going on underneath. That's not possible. You can assume some of the things and you can predict some of the thing, and based on that you are constructing the model, you are representing the natural system, right? Then models are sometimes simplistic. They can be very simplistic, okay? And as I said, based on assumption, okay? Then some of the mathematical models requires very complex calculations, right? Because some of the natural system phenomena, you need lots of calculation and equation to represent those. So that can be tedious. So these are some of the limitations of scientific modeling. Okay, so how do we model the natural system? Okay, so in the next few slides, I'm going to talk about the modeling of natural system, or how the natural system model works. Okay. Okay, so this is an example of a physical model, okay, of the natural system. You may have seen this sort of model in schools or maybe in museum or in colleges, right? So right here, what I have a groundwater flow model. Okay, so why we use that? For better overview, right? Because you can see the cross section. If you can follow my cursor, you can see different part of the groundwater system. There are unconfined, confined area. I'm gonna talk about these things later on in my presentation. And there are representation of wells, these vertical lines you can see. Some of them are injection wells. What they do, they inject pollutants to see how that pollutants going to flow, follow the paths. Okay, so from the upstream to downstream, all the way to the left of your screen, how the flow pollutants going to flow in this system. This is how you can physically represent. Okay. Okay, then you have mathematical models, and these are very popular in natural system engineering or science. So in the mathematical model, as I said earlier, you represent different variables, you use a sets of equation, and you use mass balance equation to find, to construct the modeling system. And I'm going to talk about the mass balance equation later on in my presentation. Okay. So mass balance equation or mass balance. What is mass balance? So mass balance is basically you are accounting for material entering and leaving a system. So I have a simple illustration right here. If you are following, so this is basically an open box, and there is an outlet at the bottom of this open box. So water is coming from the top from this tap and going out through this outlet. Okay, so mass balance is equation, or mass balance is something you equilibrate all the inputs and all the outputs. So in this system, all the inputs will be equal to all the outputs, right? Okay. Okay, but if there is more water coming in, less water going out, there will be change of storage as well in the system, right? Okay. So mass balance, as I said, is very important in mathematical modeling of natural system. Okay. So any questions regarding mass balance? You guys may have done mass balance equation for your chemistry class in high schools or in colleges. So this is something similar. Okay, all of your inputs should be equal to all of your output. If not, there will be change in storage in the natural system. Okay, like the one that I'm showing here. Okay. So I know I didn't give you much of a background for your groundwater knowledge or basics, or but I want to see what is your basic knowledge before giving you the brief about groundwater system and some of the basics that I'm going to talk about later in this presentation. Okay, so in this exercise you're gonna write down mass balance of this natural system. Okay, so I'm going to share a link with you. Okay, and if you follow that link, it's going to open up a form, and there is a question in there. You have to create a mass balance equation using all the inputs and outputs. So let me give you a brief before I can before I share the link of this exercise. So first of all, the black dotted line, think of that as a natural system that's a closed system, like the one that I have shown, the box that I have shown in the previous slides. Okay, so think of what ways the water can come into the system and what are the ways or variables in scientific terms, that can go out of this system. Okay, so let me share with you the form. Let me see. Okay. Okay, I have just shared the link of the form in the chat box. Everyone got it? So if you open up, it should look something like that. Okay, so I have a question. The illustration is over there, And I'm going to go back to my presentation so that you can see that as well. Then spend a couple of minutes and think about all the inputs and outputs, and create a mass balance equation. Okay. So on the left hand side of the equation, state all the probable inputs, and all in the right hand side of this equation, you are going to write all the outputs. Okay, something like, hey, my variables are A, B, C, and D. So the equation will look something like A equals B plus C plus D, or A plus B equals C plus D. Okay. So everyone has this link and opened up the link properly?
Yep.
Yes.
Great.
Is the picture supposed to appear in the form?
Yes, but this is the same picture I'm showing you right now in my presentation. So if that doesn't open or too small, feel free to take a look at this that I'm showing. So you are watching. I guess you can do that simultaneously. Watch my screen as well as go to that form. So if you have any question, let me know. As I said earlier, I know I didn't give you much to think about, what would be the actual inflows or outflows, but I just want you to, think about what it could be, right? Without knowing much about groundwater. I don't know, maybe you know quite a bit about groundwater, all the inflows and outflows, but if not, I'm not, expecting anything like this, since I haven't go through the groundwater basics yet. I'll give you another minute to write it down. Okay. Let me see. Okay, a few more seconds, then I'm gonna close this down. Okay. Okay. Rate of precipitation equal to rate of evaporation. Okay, that's a good one. Precipitation plus water from the river and ocean equals evaporation and human extraction. That's a good point as well. Okay. No, these are good. Okay. Surface, groundwater inflow, groundwater outflow, precipitation. Okay. Okay. No, that's pretty good. Yeah, more than what I expected, but yeah. So now I'm gonna talk about, give you some groundwater basics, and then let's see how you do in the same exercise once again. Okay, so what happens if it precipitates? Some of the precipitation, if it's like there are compacted areas and stuff like that, like concretes and the parking lot, what would happen? some of the water, since they cannot infiltrate, they're gonna go over the land, right? You call it Horton overland flow, okay? Then if the land surface is penetrable or permeable, in other words, there would be shallow subsurface flow, and there would be groundwater flow that will replenish the groundwater system, right? Then there is saturated overland flow. What does that mean? If it precipitates, it's going to saturate the land first, then there would be overland flow, okay? And water table is the top of the saturated part of the groundwater system, okay? The dashed line that you can see here. So what is groundwater? So typically groundwater means any water that is in underground, right? So that can be anything from water flowing through pore spaces. Pore spaces, there are like, you know, spaces between the soil particles. We call them pore space. And any water flowing through those pore spaces, any soil moisture, any frozen, in permafrost, those water are groundwater as well. Then any immobile water in bedrock. Okay, bedrock is like one of the initial component of the weathering system. Okay, like it starts from bare bedrock, then it like weathered, and it becomes like sedimentary rocks and other kinds of rock. That's a whole chapter altogether. Okay, and then there can be deep geothermal water. Okay, but we are preliminary concerned about the blue area, the saturated zone. Okay, because this is the area where you can extract water economically. Okay, so when we do groundwater resources modeling and those kind of things, we mainly concentrate on this saturated zone. Okay. Okay. So I am going back to the same illustration, and there is another illustration I am showing on the left. So if it precipitates, okay, the saturated zone, okay, which is equivalent to the aquifer, and there is the unsaturated zone. Okay, what happens? There can be overland flow, like I have shown you in the earlier illustration. Then there can be evaporation as well as transpiration. Okay, so the water will evaporate from the land surface and transpire by the trees. Okay, those term together is known as evapotranspiration. Okay, then there can be base flow. Okay, that goes in between the goes on top of the aquifer layer or saturated zone. And there the precipitation, some part will recharge the aquifer, and the groundwater table or the level will go up. And then there will be groundwater flow that will go to the stream system or the river system. Okay. And of course, we human being, we extract waters that is known as withdrawals. So I'll share another link. So this time around, I know you did a pretty good job in the first one, but I want to see if you can add something to the earlier mass balance equation. Okay, so I have just shared another link, so you can open up this form and it should look something like that. So my question is, with a few groundwater basics that you just had, create another mass balance equation using all the inputs and outputs. So basically the same questions with a little bit of knowledge. And if you have any questions regarding those groundwater basics, let me know. Then, write down the mass balance equation once again. Do you see the link in the chat box that I have just shared?
Yeah, I did.
Okay, good. So take a couple of minutes, and write down an equation. I see one of you precipitation equal to evaporation or evapotranspiration plus withdrawals. Good points. So I'll give you a few more seconds to finish up the equation. Okay, I have all of your responses. Okay.
Hey, Sanmar.
Yes, go ahead.
Would you include the recharge rate in the outflow? The output, sorry.
Okay, let me try to go back to the illustration. So recharge would be, that's part of precipitation, right? Because if you are saying your input is precipitation, because that's the input right now I have, okay? And everything else is either part of precipitation. Of course, everything is part of precipitation because that's the only input. So what do I mean? Like if you say recharge is also part of input, then you are calculating this amount twice. Okay, because the only input I have here is precipitation. Okay, then the output should be like anything. Think about this whole thing, that is diagram. Okay, the groundwater system, a closed system. Okay, what is going out? Because recharge is not going out, right? The groundwater flow is going out. Okay, recharge is replenishing the water table. Okay, so the output would be your groundwater flow, your base flow, okay, and your any flow or overland flow or runoff from the land surface, okay, and evapotranspiration as well as withdrawals. And your input would be precipitation in this case, okay. Any questions regarding that? Does that answer your question, Jacob?
Yeah, thanks.
Okay, you're welcome. Like we do not want to account the same thing twice, okay. That was the point. Okay. Okay. So now I'm going to give you a specific example of modeling, okay, and how we start modeling a natural system. What are the processes, and you know, how do you end up? What are the results we can get from this modeling system? Okay, so this specific model is variable infiltration capacity model. Okay, this is a macro scale hydrological model. By macro scale, I mean like this is a large scale model. It's usually works well with watershed scale. Do you guys know river basin or watershed? What is watershed or river basin?
Isn't it the water that would like flow into the river from a certain area?
Exactly. So the watershed is basically like if it precipitates in any of those area, it will go into a certain point and leave the whole watershed at a certain point. Okay. So that's what watershed is. So WIC is good for a WIC is a micro scale or large scale hydrological model. Usually works well with watershed scale. Although there are examples of like smaller scale application of this model, but usually they work they call it a macro scale hydrological model. Some of the key feature, the water and energy balances are simulated in this model. That's why I talked about the mass balance equation. So the energy and water is also calculated, and balance is simulated. So you use grid cell like the one that I'm showing in this illustration on the right. So this is you do grid cell based analysis. So each of these grid cell is like representation of a chunk of the physical area. Okay, say my grid cell is 10 kilometer by 10 kilometer. You can think of, say, I have a, I don't know, 10,000 square kilometer watershed area. So how many of these grid cell I'm going to need? Okay, so all of them, if are separated, that's gonna look like this. And for each of these grid cell, the model is going to calculate the water balance as well as energy balance. Okay, that's something unique about this model. Some of the standard inputs are land cover, soil. Then we need some weather data like precipitation, air temperature, wind speed, radiation, atmospheric pressure, vapor pressure, and such. Okay. Then, of course, non-meteorological data would be vegetation. Okay. We all need all this because we need to know all the inputs and outputs from this system. Okay. Like how much water is transpiring, that's why you need vegetation. How much water is like obstructing in the canopy of the vegetation, how much precipitation. So all those calculation is done in this model, and then you get the water balance and energy balance. Okay. Any question about that specific model and Okay, if not, so how we are going to represent groundwater system in this model? Okay, so what we are doing, we are creating some groundwater related pathways because we need this. We need to know the inputs and output from this system. Okay, so I have groundwater withdrawals, that is W. Okay, that's one of my output. Then I have recharge. Okay, the amount of water that's recharging the sand and gravel aquifer layer. Okay, because we are interested mainly in the this saturated or aquifer layer. So we need to know how much water is recharging that. Then we need to know how much water is going out from this aquifer. That is my groundwater flow. Then also any non-consumptive groundwater withdrawals return to surface runoff. By that, what do I mean? Like we are withdrawing water, right? We say for irrigation, I am withdrawing 100 gallons of water. Then most of the water will go to the surface, nearby surface water, like the rivers. It will stay in the system, right? So we are not consuming that part. Okay. Like another example would be the hard thermoelectric power plants. They use lots of water. Okay, but most of them, they go directly to the surface water system. Okay, so we are also calculating that part. Okay, so the first modeling process is the aquifer layer that I'm showing right now. I need to represent that. Okay, so to do that, what I do, I have to look for data and information. There are information about the thickness of this layer. Okay, these are sand and gravel deposits, and they make good aquifer. Okay, you can extract groundwater viably, economically from these layers. Okay, so there are information about the thickness of this layer. So I use this information, then I try to incorporate. If you can see the rightmost figure, I'm incorporating this information from the middle or from the left of the illustration. So this is basically I'm dividing the whole area into grids, and saying, each of the grids has a thickness, that particular layer has a thickness of that many feet or that many meters. Why do I need that? Because that specific layer is going to hold the groundwater, right? So that's why it is important to know the how thick the layer or thin the layer is, right? So that's first part done. Okay. Then I have some water management related model inputs. Okay. I talked about the water withdrawals. So how do I incorporate that into this modeling system? Because this is a grid-based modeling system. What do I do? There are information from Indiana Department of Natural Resources, that's IDNR. So they have the data for mean monthly groundwater withdrawals. Okay, so I take those data, then I use GIS. Okay, then I internally compute, okay, uh, this information. So what are this information? In each specific grids, how much water is withdrawn, okay? So basically I had county level data for water withdrawals, okay? So I had those GIS file, then I split those up into grid cell, okay, and come up with this information, because otherwise I cannot incorporate like this information in the modeling system, because the modeling system would only know the numbers for each of these grid cell, because each of these grid cell, okay, each of this square has a specific number or grid code, okay, and for each of this grid code I have a soil file that I have the aquifer layer depth or thickness information, along with other information like soil thickness, uh, and the physical properties of these layers, all those information. Then I have for the water management, I have this withdrawal information, and then non-consumptive water, those information as well, like I talked about a few minutes earlier, like uh, agricultural water is not all consumed, and then thermoelectric power plant, they do not consume all of the water, most of them go back to surface water. So those information is also incorporated so that we are not calculating the same water twice. Okay, then I model using different model scenarios. If there is no withdrawals, because I need to know if there is no withdrawal, how it look like. Then with observed withdrawal, like right now, how much withdrawal is going on, and I need to incorporate that information and see what is the groundwater level right now. And then I have to calibrate the model. I am saying, and my model is saying the water level is 5 meters below the land surface. But when I see the observation data, it doesn't match, right? So that's not going to work then, right? And I have to stop right there, because I cannot go with the projected water withdrawal and predict future, since the present is not accurate. Okay, any question about the model that I'm talking about and like how the whole process of modeling? This is one example of natural system modeling. To be specific, groundwater resources modeling, but there are hundreds of other models as well. And you can come up with your own modeling system, but the basic procedure is something like that. You identify the variables, you come up with a different equations, or there will be already developed equation, and the model will use those and give you the output information. Any question? Okay. So I touched a bit. So what I said, when I use the observed withdrawals information, okay, then I need to calibrate the model. Okay, so by that I mean like some of the parameters, like I am saying, say the flow capacity of this specific layer is 10 millimeter per second or something like that. I'm just giving you a rough, example. But that didn't work well, okay? That's why maybe the water level is 5 meters below the land surface, but I have some observation data to look at, and that says it's 7 meters below the land surface. So I calibrate those groundwater variables or parameters, okay? So I tweak those data and information based on the references that I have. There are lots of USGS, United States Geological Survey reporting documents. There are lots of textbook as well. You go and use those references and, come up with a new value and calibrate the value and run the model again to see like your calibrated model is close to the observation data or not. Calibrated output is close to the observation or not, okay? So this is something called calibration, and this is a very common part of the modeling process and very important part, I'll say. And some of the parameters that you can calibrate, for example, infiltration, base flow that I have shown, soil moisture, it can be the soil layer thickness, and saturated hydraulic conductivity, that means how fast the water is moving through the pore spaces of the soil. So all these parameters can be calibrated to match the observational data, okay? Okay, then you will compare this simulated information. One example I have said is groundwater table or groundwater level, that is depth of water from the land surface. Other examples of this variable would be, we can calibrate for stream flow, right? We want to know, I know the groundwater table that looks pretty good. What about stream flow? What about runoff? What about recharge? Those things should have to look good as well, okay? Because one is connected to another, and if you can recall, we are talking about a whole mass balance. So all the inputs should be equal to all the outputs. So that's why we need to compare the simulated values with the observed values, okay? And after calibration. So after calibration is done, you can validate the model, okay? What does that mean? Say you have calibrated for 10 years, say from 2000 to 2010. From 2000 to 2010, you have simulated with all the information and you have calibrated these parameters that I have just mentioned, and it looked good. Okay, it looked good. Your groundwater level that matches the observational data, that's fine. Then what you need to do with the same parameters, you are not changing the values anymore. Okay, with the same parameters, with the same values, you run the model for a different time frame. Okay, say from 2011 to 2020, and if that looks good, this process is called validating your model. So we are trying to validate like with the given parameter and given, after calibration, if I use for another time frame or maybe for another area, it should be looking good as well. Okay, that is the process of validation of the model. Okay, then you can proceed with the model for other predictions and other beautiful things that you can do. Any questions regarding that? This whole process so far, calibration, validation, like how these things work? Okay. Okay. So I'm gonna give you some of the examples, like what results you can get out of the model. So this is specific to the weak model that I have shown you earlier and giving you examples for. So there are three different illustrations right here. On the left, I have the stream flow information, and on the middle I have the groundwater level information, and on the right I have the runoff information. Okay, I'm gonna talk a little bit about each of these items. Okay, so on your left in the stream flow information. Okay, so I don't know, it's hard to see. Let me see if I can pan it. I guess it's not happening. I'm sorry. Do you guys can follow this illustration? On the left I have the stream flow data or stream flow information, and there are three different lines, one for no withdrawal, one for observed withdrawals, and one for like projected withdrawals. One blue, one green, and one red dashed line. I know it's hard to follow. Okay, but if you are following along, you can see the blue line that matches the green line. Okay, but the dashed red line, this is what I'm predicting. Okay, I'm predicting the water withdrawal would be like this in the future. Okay, and that means the stream flow is also changing with projected withdrawals. Okay, then in the middle I have the groundwater table information. Okay, so there are three lines. Green one is with no withdrawals, and the blue one is with observed withdrawals, and the red one is with projected increase. Okay, so water table, what would happen? And like if you withdraw water, the water table will go down, right? So I have projected that with projected increase in the future. Okay, if we model that for the past period, the water table, the bottom line, the red line, that's below the other lines. That means the water table is below the other lines. That means water level went down. Okay, if there is predicted increase in water withdrawals. Okay, then on the right hand side, I'm showing the difference between projected withdrawals and observed withdrawals, and that's impact on the total runoff. Okay, so you can see there are differences. Okay, as much as 10 millimeter. Okay, so this is given in terms of thickness of runoff. So in some of the areas in the water, river basin that we are situated, that's Wabash River Basin. So in this watershed, the total runoff difference would be there if we continue to, withdraw water at the same rate if we are doing. Okay, so this is just showing you some of the examples. What can we do with the output of these models? Okay. Any questions? I know
Is it better to have runoff, or is that bad?
I'm sorry. Is it better to have runoff or not?
Mm-hmm.
That was your question. Okay. So that's a very good question. First of all, okay. So more runoff, that means water is not penetrating, right? Because you have compacted land or maybe some impermeable land, right? That's why most of the water is, running off from the surface. So that means there is less chance of the water to go and infiltrate and recharge the aquifer. Okay, there's our say the aquifers are the saving accounts of groundwater. Okay, if I can correlate. So having said that, coming back to your questions, so more runoff, that's not good for a couple of reasons. Then we are gonna have less recharge. Okay. The second thing is more runoff means like all of the water running off from the concrete and compacted or impermeable land, there will be gushing out from the system, right? That's why you see the flash flood. Okay. All the roads after like heavy rainfall, they are inundated because of all the runoff from the compacted area. Okay, and we do not want that, right? That's why the flood happens usually, okay? Especially the flash floods one, okay? Does that answer your question?
Yeah.
Okay, cool. Okay. So I have another small exercises for you. Spend a few minutes on this one, then we should be we'll be done with this skill session, okay? So this is another mass balance equation I want you to write down, but this is for a river basin. So the river basin is a like specific contained area. Like if precipitation occurs in any area, you know, the red line area, okay, that will go out in this outlet if you are following my cursor, okay? So any precipitation going in this system that will only go out through this location, okay, if it's not recharging the aquifer, okay. So this is my river basin. This is a contained area. I need this because I am doing some modeling. That's why I have to specify the area, okay. So say the annual precipitation for this area is 1000 millimeter per year, okay, and the average stream flow going out of this system is 400 millimeter per year, okay. So right now think about all the inputs and output for this system or for this basin, the red line area, okay, and write a mass balance equation, okay. And I am giving you another situation. Say that there is a people have constructed a dam or a reservoir right here, okay. So due to the construction of this dam, what would happen to this area? Like some of the variables or some of the inflow or outflow parameters, what would happen to them? Okay, think about this, and let me share the link for this third small exercise so that you can work on that. Let me go back. Okay, so I have just shared the link for this exercise in the chat box. Please open that. As I said, I have a couple of questions. In the first one, write a mass balance equation, a water budget for the river basin, you know, and try to allocate number. I know I gave you some number, precipitation and stream flow. So think of in terms of what would be your inputs and what would be your outputs. Try to allocate some numbers. If precipitation is your input, that's 1000 millimeter. Think of any other inputs right here. If not, what are the outputs, and you know, try to allocate some numbers. And in the second question, I have the situation, as I said, a dam or reservoir has been constructed in this area. So the quantity of what components would go up or go down, okay? In which of these components you will see changes, okay? One clue, precipitation would be still same on average, right? Okay. Then think about some of the parameters or variables that can increase or decrease due to the construction of this dam. And what about the overall storage? Okay, so think this and write down your answer pretty quickly. I know I'm running out of time. Let's see. Everyone has the link, right?
Yep.
Great.
Hi, Sanoar.
I'm sorry.
Is it fine reading right now because I've got different.
I'm not sure I got it. Can you say that again? I'm sorry. Really breaking up.
I'm just saying that is it fine if I leave because I need to get somewhere?
Oh yeah. Go ahead. Yeah, sure. Yeah, I know I'm
Thank you.
running over that. Thank you for joining us. Thank you. Appreciate that. Okay, I see your responses. Okay, 1,000, 4,000 plus accumulated precipitation, evaporation plus. Okay. No, okay. No, you got the point. You got the whole point. One more thing would happen, like since the surface area of water is increasing because of the reservoir or construction of the dam, what would increase? Evaporation will increase, right?
Gotcha.
Okay. I'm sorry.
I said gotcha. Sorry.
Yeah. And you are also right if you said like the storage, like the water content in this area is also increased. Okay. Okay, having said that, I think that's all I had. Thank you for joining in. If you guys have any questions, like, you want to know more about the modeling system, specifics about big modeling, feel free to email me. My email is rahman17@purdue.edu, as you can see in the screen. And if you do not have any further question, I'm gonna end this meeting, and everyone have a nice rest of the day, and yeah.
Thank you.
You're welcome.
Thank you.